Microbiology is one of those areas where historically we've done things the same way for more than 100 years. If you look at many of the technologies that we use today, streaking plates with calibrated loops, doing biochemical identification, even most of the forms of susceptibility testing are very old forms and they haven't really changed. And so as I look at, I think my responsibility when I make presentations like this or when I visit your hospitals, it's to sort of look at where we are today and where we can go in the future. And so that's what I'm going to focus on. So as I start with bloodstream infections, I will also talk about where I think the future is going to go. Now, bloodstream infections, to put it in perspective, becomes really quite critically important. Sepsis is estimated to cause about 30 million cases a year globally, and about 6 million people die due to sepsis. It's one of the leading causes of death, medically related deaths. Interestingly, only about 1/3 of the patients that are septic will have a positive blood culture. And I'll talk about some of the reasons for that and what I think are some of our responsibilities to do a better job to be able to have more positive blood cultures. That becomes important because a positive blood culture is really fundamental to treating those patients. And the better we're able to treat the patients, the better the outcome is going to be. Now, just to illustrate that, I'm going to cite two studies. I'm not going to throw lots of numbers at you because I think that sort of overwhelms people and we lose the value there. But what I'd like to do is give you some overall perspective. The two studies I'm citing are both meta-analysis where they looked at the literature and critically analyzed the literature. In the first study, what they did is they reviewed 70 published reports, clinical studies, that looked at the efficacy of empiric therapy. That is, you suspect your patient has sepsis, and you empirically give antibiotics that you think should be appropriate for treating that patient. When they looked at these 70 studies, they found on average just under half of the patients received inappropriate antimicrobial therapy. And the result of that was about 1/3 of the patients died of their sepsis. So we're not doing a very good job with our empiric therapy. The second study looked at 60 publications and specifically looked at the impact of empiric therapy on survival of sepsis caused by gram-negative bacteria. And what they found was that inappropriate therapy in these studies was responsible for more than a 3-fold increase in mortality. Now, how do you avoid empiric therapy? You do that by having a positive blood culture, or at least having definitive evidence of the organism that's responsible for the infection. So it underlines the value of doing accurate diagnostics to support the empiric therapy of these patients. Now, I'm going to start not with blood cultures, but actually some biomarkers that are used to predict that a patient is septic, because many times that's very difficult to tell, particularly in the early forms of sepsis. It's difficult to differentiate an inflammatory response due to sepsis or an infection versus an inflammatory response due to some other event. And obviously, if it's not an infectious cause of the inflammatory event, you don't want to treat the patient. So in order to avoid unnecessary therapy, we would like to have biomarkers that predict that this patient who has inflammation due to an infection and is at increased risk for developing sepsis. Now, there's been a number of biomarkers that have been evaluated in the literature: procalcitonin, C-reactive protein, expression of CD64, but all of those have been found to be relatively nonspecific as the initial predictor of sepsis. They can be used to monitor sepsis, but not as an initial predictor of sepsis. But there was a very interesting study that looked at septic patients, and they compared them with normal patients, and they looked at more than 100. All right, we're having a light show over here. They looked at the expression of more than 100 genes in this population of patients, and they found that many didn't change in the patients as they developed sepsis. Some of the genes expression increased, and in some cases the gene expressions decreased. And they found 4 target genes that were particularly useful to evaluate. And I list them here. I'm not going to go through names. I don't think it's particularly important. But just the concept that there are 4 genes, 2 of which had increased expression in septic patients and 2 had decreased expression. Now, I'm sorry, I went the wrong way. If we look at these genes individually, I have 4 columns in the figure to the left. Let's see. That really doesn't do much as a pointer. So to the left you see 4 columns with a series of dots. The red dots are patients that developed sepsis. The black dots are patients that did not develop sepsis. And if you look at the first column and the third column, you see that the black dots are at the top of the figure, the red dots are at the bottom. And if you look at the second column and the fourth column, that reverses. But as you look at each of the individual ones, there's a great deal of overlap. And this was some study actually that BD did about 10 years ago now. When we looked at that, we said this isn't useful, and we stopped that project. Well, this group, an independent group, is actually much brighter, I think, than what we were at the time. And they said, why don't we look at the ratio? So they looked at the ratio of one of the genes that was overexpressed to one gene underexpressed, and they added that to the other 2 genes, one overexpressed and one underexpressed. And then they came up with a figure that's on the right-hand side. And in this case, you see all the red dots are on top and all the black dots are on the bottom. So in other words, with a relatively simple mathematical formula that really should have been obvious, they're able to differentiate between patients that have impending sepsis versus patients that didn't. Now, I should say, I didn't make this maybe clear, these are all patients very early in the development of their inflammatory response. So at the time, there's really no clear clinical way of saying which ones are going to be septic or not. This tool allowed them to do that. So what it allows them to do then is to say these patients are at high risk and should be considered prone for developing sepsis and managed very differently from the patients that are at low risk. I think we're going to see a series of these types of biomarkers used to accurately predict patients at risk for sepsis. And that in and of itself is going to improve survival, because the key component for a patient to survive sepsis is to have an early diagnosis and initiation of therapy. So biomarkers, I think, are going to become quite useful in the future. Now, there's also a number of molecular approaches that have been attempted to detect organisms directly in the blood, so you have a very specific diagnosis even without culture. What I've done is I've cited 4 of those studies for the systems, and I'm going to show the limitations of 3 of the systems. The first is the Cobas Septifast system. It is a relatively labor-intensive procedure. Takes anywhere from 4 to 7 hours from the time you take a blood sample to you extract the DNA that's in the sample of the organisms, to amplify that DNA, and then to be able to specifically identify the organisms that are in the bloodstream. This system, as I said, takes 4 to 7 hours. It requires batching to be done. And so, in reality, if you ignore the expense of the system, it just isn't practical. Because what you want to be able to do is, much like the biomarkers, run a test on an individual patient at the time you suspect they have sepsis so you can manage that patient. So this is a system that does have clearance in Europe, does not have clearance in the United States, and really has not been very successful, although we still see some occasional reports about the Roche Cobas Septifast system. So this is not a system that I would recommend for detecting septic patients early. Abbott also developed a system called Iridia. It's a different approach. What it does is that it takes the nucleic acids and it amplifies the nucleic acids that are targeted for bacteria or yeast that could be in the patient's bloodstream. They look at sequences of the nucleic acids not by sequencing, but actually by mass spectrometry. The advantage of this system is that rather than being able to identify 10 or 20 organisms, it literally can identify thousands of organisms, and it would include bacteria, yeast, and viruses. So in theory, it becomes quite attractive. But again, it's labor intensive, very large and expensive instruments that are required to do this procedure. It requires batching of the test, and again, a long time before the results are available. Abbott has worked with this system for about 10 years. They acquired it from a California company. And I believe today that although it was initially CE marked for European sales, it is not being sold anymore. So what I wanted to show you was two different approaches that had some inherent limitations. Expensive equipment, still labor intensive, long time before you have results in terms of hours, and it required batch testing. So none of those features are what you would want to have for a system to detect organisms directly in blood. There's there's one other system, T2 Biosystems, that has developed a panel for detecting yeast in blood. It does it in a little bit shorter period of time, 4 to 6 hours. You run the test individually, so you don't have to do batch testing, but the instrument that I'm showing here is what you would use for a single test. And because of the amount of time it takes to run a test, you can only run 1 or 2 samples a day on that instrument. So if you're getting many blood cultures into your lab, you'd have to have many of these instruments. So again, not a very practical approach to diagnosis of sepsis. In this case, specifically for 4 species of Candida. The system that I think is quite interesting was developed by a Canadian company. It's called Qvella. And what they're able to do is take host cell and free DNA that's in the bloodstream and eliminate that to concentrate the organisms and then to lyse the organisms by using an electrical current. The the ribosomal RNA that's released from these organisms is then amplified, and they're able to identify roughly 20 organisms in a sample. It's a very rapid test. It takes about an hour. It's a very inexpensive test. The consumable components are quite inexpensive. And the instrumentation, although it's still in development, we would predict that's also going to be inexpensive. So here you have a relatively inexpensive system that does not require a lot of labor. You get results in about an hour, and you can run them as the samples come into the laboratory. Now, this is a system in development. We probably will not see it for another 2 years where it's in actual clinical use. But I think this is the precursor of what we're going to see in the future for rapid diagnosis of septic patients. Will this replace culture? No. You would do it in combination with culture because you still need to get the empiric antibiotic. You need to change from empiric antibiotics to directed antibiotics. But I think this becomes a quite attractive approach to supplementing the way we diagnose sepsis. So what I wanted to do is to show you biomarkers, to show you some molecular approaches to doing sepsis diagnosis. And now let me go into an area that maybe it should be probably more familiar to you, and that is the use of blood cultures in septic patients. Becton Dickinson has been involved with blood cultures for many years with a number of automated platforms that they've developed. They were the first to launch an automated blood culture system back in 1968. They were the first to commercialize the use of resins in blood culture bottles in 1981. I'll come back to resins in a minute. They developed the first lytic anaerobic formulation of media in 1997, developed an automated way to monitor how much blood was in the blood culture bottles, and they've developed a system that can be used as satellite tests. I'm going to touch on each one of these points over the next few minutes. If we think about blood cultures, we should really think in terms of looking at this in a very simple, straightforward way. A successful blood culture is really defined by two things. You want to isolate the most organisms possible, the most different organisms, and you want to do it as fast as you can. So as we compare one blood culture system to another, one blood culture bottle of media to another, the question that we always have to pose is, are we detecting more organisms, and are we detecting them faster? Now, the success of being able to do that is determined by a couple of factors. One is the media that you use. The next is how much blood you put into a bottle and how many cultures you collect. And the last is, what's the minimum time, not for detecting an organism in an incubator, but the minimum time from when the blood culture was collected until the physician has a result. In the laboratory, we all too often focus about what we do in the laboratory, but the real value is what happens before we get the culture, what we do in the laboratory, and how fast the physician sees that culture result. And so that's, as we think about how we're going to fundamentally improve blood cultures, we have to have a much broader view than what we do historically. Let me start with the first concept, that is processing blood cultures. If we think about it, we have the physician that orders the test, the phlebotomist that cultures the blood or draws a blood sample. That bottle or bottles are sent to the nursing station, which then transfers the bottle to the laboratory. The laboratorian acknowledges in the computer that they've received a blood culture, and they put the bottles in the incubator. After a period of incubation, the positive bottles have a signal that says it's positive, and the bottle has to be removed, and we do identification and we do susceptibility testing. So when we think about what we do in the laboratory, we really only control from the time we receive the culture in the lab as we go through all the processing. So if we're going to look for opportunities to improve what we're doing, we have to look at opportunities how to shorten the delays at each one of these steps. Now, I think it's important to appreciate how bad the delays can be. And this was a study that was done in the Netherlands, and there's been a couple of other studies that have done the same thing. So I'm just citing one study. And they looked at the transit time from the collection of the positive blood culture bottle to when it was received in the laboratory. That's not when it was put into the incubator, just simply received in the laboratory. And they found that in their experience, the average time was about 3.5 hours. More importantly, they looked at areas where it was particularly long, and in their hematology and oncology unit, they found that the median time from collection to receipt was 12.5 hours, and from the emergency department, it was 16 hours. And it's somewhat logical why there were delays. They found the delays were associated with areas of the hospital where there's a great deal of activity in managing the patients, whether it's distance from the laboratory, and the time of day or night when the blood cultures are collected. What this allows us to do then is to start thinking about where are the areas that we need to focus our attention to reduce this delay that we see here. And so there's a couple of studies that have been done to look at this. We just finished a study with one of our businesses, MedMine, that allows us to track a patient from the time they come into the hospital to the time they leave. We can look at all of the diagnostics that are done for that patient, look at all of the pharmaceuticals that are ordered for the patient, and look at the response to test results from the laboratory in terms of how they use those results to manage the patient. And we're doing a study with this looking at our lab automation system, the Keystra system, but I posed the question, can we just look at blood cultures to see what the impact is? And so over an 18-month period, we looked at 13 U.S. hospitals that were part of this MedMine network, and we analyzed all of the blood cultures that were collected from those patients. There was over 165,000 blood cultures that were collected, and about 10%, 9.5%, or over 15,000 were positive. So we looked at those positives and we said, how much time from when it's collected to when a gram stain is performed? And on average, it was about 20 hours. We then said how much time between collection and when the identification was reported. It was 1 day longer. And when we looked at from collection to when the susceptibility reports were issued, it was 2 days longer. When we looked at this a little bit more carefully, we analyzed actually when were the reports issued. The orange bar each of those four groups represents work that was being done during a 6-hour period. So the first one is from midnight until 6 in the morning, the second from 6 until noon, the third from noon until 6 in the evening, and the last one from 6 in the evening to midnight. The orange bars, the one on the left side, represent when the blood culture was processed, was when it was collected. And what you see is blood cultures are collected throughout the day and evening. Now you would suspect, if all things were created equal, the gram stain report, the identification, and the susceptibility reports should follow those, should have a similar distribution for all the blood cultures. In fact, that's not the case. If you look at the second set of columns, what we see is that, and this is from 6 in the morning until noon, we see the gram stains, about 43% were reported during this period of time. Identification, 78% were reported during this period of time, and susceptibility tests, more than 80% were reported during that period of time. In other words, the results are being reported at the convenience of the laboratory and not at the need for the patient. So we need to start looking at how we can start processing these specimens as rapidly as possible. Now, one way is to shift to a 24-hour service. A 24-hour service, and that's what was done in this hospital. The blue bars represented the work that was being done in 2013 before they had a 24-hour shift. And what you see is almost 80% of the identification reports were reported in that 6-hour period between 6 o'clock in the morning and noon. When they shifted to a 24-hour-a-day shift and said that all of the work would be performed during all hours of the day, evening, and night, what you see is a more uniform distribution of reports based on the orange bars that we see in these graphs. And the figure on the right-hand side shows when the final reports were being issued, and you see a shift to the left. In other words, earlier reports are coming from the laboratory. Now, I illustrate this point with these figures just to say that we have an opportunity without changing any technology at all to do things better. Your lab may not be able to go to a 24-hour-a-day shift like this laboratory, but if we just focus on performing work for at least this specimen where it's critically important, then I think we can get results to the patient much faster than what we've done historically. So that's looking at opportunities to do a better job even without changing the things you do in the laboratory. I'm going to go back to a figure I skipped because I wanted to show one other point. And this was the Canadian laboratory that said, we know we have a delay in getting specimens from the emergency department to the laboratory. And it was roughly a 2-hour delay, so it wasn't even as severe as what I described with the Dutch study that was done. And what the Canadian laboratory did, in order to eliminate that 2-hour delay, put one of the small BACTEC instruments in the emergency department. So when the cultures were collected, they were put directly into the incubator rather than waiting to have somebody take them down to the laboratory. And what they found was that it had greater than a 2-hour reduction in time to positive cultures just by making that simple change. So again, it's not that they're using new technology. They're, in this case, they're applying it maybe a little bit differently, but they just looked at where are our problems and how do we solve them. And again, I would say that that's something we should always be asking. How can we improve the quality of care we're providing in this microbiology lab? Now, I said 1/3 of the patients with sepsis, only 1/3 had positive blood cultures, and there are some reasons for that. The first is we probably don't collect an adequate volume of blood. This was a study in the upper left-hand corner. We see a graph that looked at the number of the amount of blood put into a bottle on average. The axis on the left is the number of bottles that were received in the laboratory. The axis running along the bottom is the volume of blood put into the bottles. And although you certainly can't read the numbers under there, on average where that circle is, it's about 4 to 5 milliliters of blood was put into the bottle. The red arrow indicates the volume that's recommended, 8 to 10 mLs. So about half of the amount of blood was put into those bottles. The graph below that is a summary of 3 studies that were performed looking at the impact of increasing the volume of blood. And what they see is a dramatic increase in positive cultures as you collect more blood for those bottles. And then the figure, the bar graph that's to the right, was a study that was done in Turkey, and they converted the way they were doing testing from a single bottle to using 2 bottles per culture to using multiple cultures. And what you see is as they did that, they saw more positive blood cultures. So if 2/3 of our patients have a negative blood culture when they're septic, this is probably the major reason. We didn't collect enough blood, enough bottles, and enough cultures in order to make the diagnosis. And so I would challenge you to say that if we're going to do a blood culture, let's do it right and be maybe more selective in which patients get blood cultures, but the ones that do, we should make sure that we have an adequate culture in order to make the diagnosis. The next point that I'll talk about is the media that's used. I'll start off with aerobic and anaerobic media. It is strongly recommended to use the combination of an aerobic bottle and an anaerobic bottle. I have challenged our marketing people to come up with a better name because I think calling a bottle an aerobic bottle or a bottle an anaerobic bottle is actually misleading. The reason I say that is that if we think about the bacteria that we isolate, we have aerobic bacteria, strict aerobic bacteria like Pseudomonas, Acinetobacter. We have strict anaerobic organisms like Bacteroides and Clostridia. And we have facultative anaerobic organisms. That's virtually the majority of the organisms that we isolate in the lab. Your Staphylococci, your Streptococci, your Enterococci, all of the Enterobacteriaceae, they grow both aerobically and anaerobically. And although it's maybe not obvious to most, the majority of your facultative anaerobes grow better and faster in the anaerobic bottles. And in fact, and it's really quite interesting because I get a chance to look at a lot of internal data from clinical trials. We see that a number of patients with gram-negative bacteremia will only have positive bottles initially in the anaerobic bottles. I'm not quite sure I understand why that is seen. I'll show you a little bit of data for that in a second, but it's really very interesting that you see that. So despite the fact we call it an anaerobic bottle, the primary purpose is to isolate the facultative anaerobic organisms. That's the first point. The second point is that resin media has been consistently shown to give you better recovery and earlier time to detection of bacteria and yeast in blood cultures. The difficulty with resin media is that it's not just removes the antibiotics, it also removes nutrients. And we've been making anaerobic media since 1982. We've been making resin media since 1982. And so we've learned that what nutrients are being removed and how to supplement the bottles in order to optimize your recovery. But it is a balance between the value of removing antibiotics and the downside of removing nutrients and important components. But having said that, resin media has been consistently shown to be a superior media. We've also done some work with lytic media. Lytic media is designed, it has detergents in the bottle, it's designed to lyse blood cells. That has a couple of important points. The first is that you have intracellular bacteria that are still viable, and you have bacteria that cover the surface of the blood cells. You lyse the blood and you release those organisms. So right from there, you're going to have more organisms to start growing in the bottle. That lysis also releases nutrients that are in the blood cell, and that supplements the nutrients that are naturally in the media, and so you get better growth of organisms. And finally, the blood culture systems that exist today are, for the most part, measuring metabolic activity in the bottle. And as your bacteria and yeast grow, they metabolize substrates, and that's what's being monitored by the sensors that are in the bottle. The blood cells also have metabolic activity, and so we call that noise that's in the bottle. And so what has to happen is the microbial metabolism has to reach a level that's above that noise for us to be able to detect the organisms. Now, if you remove the noise, if you lyse the blood cells, then you can detect the microbial metabolism earlier. And that's what we see in the lytic bottles. So the advantage of a lytic bottle is that you've provided more nutrients, you've released intracellular organisms, and you've eliminated the background noise. So you get better recovery and earlier time to detection, which, again, remember, that's the goal of a blood culture. More organisms, detect them earlier. And so what we recommend is a combination of a resin media and a lytic media. It would be ideal if we could mix the lytic components, the detergents, with the resin media and have really an ideal bottle. The problem is the resins remove the detergents, and so you can't put them together. And that's why you have an aerobic and an anaerobic bottle. Let me show you just a little bit of data to support what I just said. This was a study looking at the value of aerobic and anaerobic media. And again, there's a number of studies. I just pull out a few of them just to illustrate the point. On the left-hand column, we have the list of organisms that were isolated in this study. This was looking at an aerobic plus resin bottle and an anaerobic plus resin bottle. And what you see is that there were significantly more organisms recovered in the anaerobic bottle for the staphylococci, for the Enterobacteriaceae, and overall growth. And also anaerobes. And so if we look at the value of the anaerobic bottle, it's to recover the most common organisms that we isolate. If we look at resins, as I said, the resin media was developed in the early 1980s to neutralize antibiotics. There are proprietary formulations of this media because, again, you're supplementing the nutrients that are being removed from the bottle. And finally, every study that's been done looking at the value of resin media has shown that it's superior to unsupplemented media and charcoal supplemented media. This was just one study that compared resin media with charcoal-containing media, and for the aerobic media, they found there was 140% more organisms recovered in the resin-containing media compared to the charcoal-containing media. They also found time to results was earlier within resin media by about 4.5 hours. And then finally, looking at the value of the lytic media, I've just highlighted in yellow a couple of points that I wanted to make here. If you look at the recovery of the Enterobacteriaceae, in this study they compared an aerobic resin media, an anaerobic resin media, and an anaerobic lytic media, and the greatest recovery of Enterobacteriaceae was in that anaerobic lytic media. The overall recovery of organisms was essentially the same for the aerobic resin media and the anaerobic lytic media. If you look at just the percent recovery of all the organisms isolated in all the bottles, 77% were in the anaerobic lytic media. And if you look at the combination of an anaerobic lytic media with anaerobic resin media, we had more organisms recovered in that combination than when you looked at the aerobic and anaerobic resin media. So overall, you can see the value of using a lytic media in combination with a resin media. Time to results, as we would have predicted from what I said earlier about the resin media, was realized here, whether we look at the mean or average time to detection or the median time to detection. It was fastest in the lytic bottle and fastest in the combination with the resin plus aerobic bottle and the anaerobic lytic bottle. So again, we see the value of using different types of media with different components that supplement them. Processing positive blood cultures. There's a number of steps that should be taken. Rapid identification of organisms with multi-mass spectrometry, rapid identification with molecular probes, detection of resistance markers with molecular probes, and rapid antimicrobial susceptibility testing. I'm going to skip the discussion of MALDI because I actually included that with my next presentation, so I'll come back to that in a second. If we look at the use of molecular probes, and this is something that now is becoming fairly common. I haven't had a chance to visit your labs, but some of the other labs that I've visited while I've been here in the Middle East and really globally, I see this, where particularly BioFire and in the United States, Nanosphere are being used to help process positive blood cultures. And these are multiplex molecular tests that can identify either a number of organisms or can identify resistance genes. Now, if you look at the value from this slide as I've summarized it, it's primarily to identify anywhere from about 22 organisms to more than 90 organisms in your sample. With multi-mass spectrometry, you can identify any organism in your sample. So I really see very little value of these expensive molecular tools to identify organisms. I'll come back to that when I talk about MALDI in the next lecture. So if you separate the identification and just look at antimicrobial susceptibility tests, or I should say detection of resistance markers, they don't do a very good job. The only one that actually detects a large number of important resistance markers is Nanosphere, which identifies the genes responsible for methicillin resistance in Staph aureus, for vancomycin resistance in the enterococci, and for carbapenem resistance in gram-negative bacteria. But still, having said that, that doesn't really give you a lot of tools. If the resistance marker is there, that's valuable, but if it's absent, then you don't really know whether the organism is resistant to the antibiotic or not. A different approach is what's been developed by a company called Accelerate, and this now has FDA approval and CE marked. It is designed to do the direct identification and susceptibility test from a positive blood culture. Now, this is different from what I talked about before, where we are detecting and identifying organisms in blood. This is, you have a positive blood culture, you're now going to work this up. It identifies the organisms, and roughly about 20 different organisms, using what's called FISH technology, or fluorescence in situ hybridization. It's a technology that's been around for a very long time. But again, I would challenge, why do we need to identify organisms with this system when MALDI will do a much better job identifying a much larger number of organisms? The real value of this system is perceived to be that you can do a direct phenotypic susceptibility test that's reasonably accurate, and you get the results in about 7 hours. However, if you took the positive blood culture and just set up your susceptibility test, whether it is a Vitek test, it is a Phoenix test, it is a microscan test, you're going to get accurate results, highly accurate results, in roughly the same period of time. Now, I should say that each instrument this is one instrument for one test, so if you have a number of positive blood cultures, you'd have to have multiple instruments. The plate that's below the instrument is the consumable that's used for each test, and you can look at the complexity of that and realize that it's fairly expensive. So each one of these tests is going to cost well over $100 US. So again, I think there are better ways to be able to do the same thing and maybe get actually more data than what this would provide. But this is something you'll see a great deal in the literature. I think this is sort of the path that people are going to be able to do direct identification and susceptibility tests much faster, or at least they think much faster than what we're doing historically. What I'd like to do is to end this discussion about sepsis by really focusing on one other thing, and that is that last step when I said, how do we communicate information better? How do we actually understand the information that we're generating in the laboratory better? And so there's, at least with Becton Dickinson, they have Epicenter, which allows you to be able to do that. I know other laboratories that have developed their own internal ways of monitoring growth and other parameters. But let me just illustrate with Epicenter some of the things it can do. So it can monitor the blood culture, or the amount of blood that's put into the blood culture bottle. And what I show in this figure is just 4 different ways of doing that, where you can look at the amount of blood that's in the bottle, the amount of blood that's coming from bottles that are inoculated in specific units of the hospital, the amount of blood in bottles that are prepared by specific phlebotomists. So in other words, you can use this type of a tool to first say, overall, do we have a problem or not? Are we underfilling the bottle or potentially overfilling the bottles? And then if we have a problem, Is it located in specific hospital sites and with specific phlebotomists? So as a laboratory director, it allows you to have tools to be able to say, I can do a better job than what I'm doing currently. In addition, there's a number of other parameters that can be examined. I'm just going to show a couple of slides very quickly. This is to be able to look at the number of blood culture sets you're receiving from patients, number of bottles per set, and so forth. You can look at workflow in your laboratory to be able to predict, can we do this better than what we're doing currently? And you can look at the platform performance, how rapidly are we getting positive blood cultures, which organisms are coming up first, and so forth. In other words, you start to collect data, and I always have found that data is really critical for me to be able to run a laboratory, in an intelligent way. These types of middleware computer tools allow you to have data to do a much better job. And then finally, you can use that data to communicate information more effectively to your physicians to help them understand what it means when you have a positive culture, or when after 2 or 3 days you don't see a positive culture and you suspect you have a yeast infection, as an example. So as I look at future needs, and this is more looking where I think we need to go in the future, we need more sensitive and specific biomarkers for early sepsis detection, and it should be a laboratory point of care device. The example I gave you of the 4 biomarkers that were analyzed to be able to predict patients in early sepsis. Currently, that's a test that needs to be run on a molecular platform that takes 2 to 3 hours to get a result. That's useful, but the real value would be if it's a point of care test where you get a result in 10 minutes. So I think there are opportunities to continue to see improvements with biomarkers. Molecular detection of bacteria and fungi in blood, directly from blood. It must be rapid to eliminate batch testing. It must be inexpensive, and it will complement culture. So the Qvella test that I showed you, I think, is a very attractive test. I am absolutely convinced we will see more of those types of tests in the future. I know BioFire is developing one. But it can't be like a BioFire that costs $150 to run a test. Because if you want to do it every time you suspect a patient has sepsis, you don't want to generate that sort of expenses. We need to eliminate the workflow delays from the time of collection to the time of final results. I gave you a couple of examples of how we can do that. Putting remote blood culture instruments in sites where we see the greatest delays, being able to modify the workflow that we do in our laboratory to improve turnaround time are just 2 examples, but I think we as people that work in the laboratory or physicians that are utilizing the data, we should demand to be able to reduce that period of time to make the microbiology results truly valuable, but also to benefit the patient, which is our real goal. We need to improve the sensitivity of the culture methods. We can do that through innovations, such as being able to concentrate the organisms using maybe even newer formulations of media. I talked about maybe trying to combine resins and detergents in order to have an optimum media. Maybe we can change the incubation conditions. It'd be ideal if we could do a better job with a smaller volume of blood, because I'm realistic, collecting large volumes of blood is a problem for many patients. So I think that we have to continue to look for ways in which we can make improvements. Adoption of existing and future technologies for rapid identification and susceptibility tests become important. Many times somebody will say, I don't care the name of the organism, just tell me what drugs to be able to treat the patient with. I think that's probably true, but if it takes from the time you have a positive culture anywhere from 7 to 20, 24 hours to get a susceptibility result, the rapid identification of the organism is important. So I think we need to continue to work to improve that. And finally, we need to optimize processes for communication of the lab results to the appropriate healthcare provider. I didn't specifically talk about that. It is a challenge to be able to get hold of the right person, but our goal should be the right report for the right person at the right time. So all of what I've talked about is steps towards doing that. I think we've made some remarkable improvements over the last decade. I'm absolutely convinced over the next 10 years we're going to see even more dramatic changes. But as people developing the test, using the test, reporting the results, using the results, I think that we have lots of challenges. So with that, let me stop here. And thank you for your attention. If you have any questions, I'd be very happy to answer them right now. I'm not quite sure how you want to do it. Questions now, or how do you want to do this? We can do questions. Okay. By the way, those that ask questions get to go have a break afterwards. The others have to sit here, no coffee. That's it.